Hi everyone, I'm Lucy Gunawan and today we're continuing our data preparation course. This time, the focus is on combining tables with join. In this tutorial, we'll review together the join concept. I'll try to make this concept as easy as possible to understand. For a very experienced data scientist, join operations are easy and are very common. But I know from experience that the notion behind join operation can be a little bit tricky for beginners in data science. So pay close attention to this video as join is a crucial concept in the data preparation and analytical field. The join operation is also fundamental when working with relational databases. It allows you to combine rows from multiple tables based on a related column between them. By joining tables, you can extract meaningful information between different data tables. Joins are also used to enrich datasets and clean datasets. They are literally everywhere. This tutorial is slightly longer than the previous ones because we adopted here a slower pace with a lot of small examples just to make everything crystal clear. Indeed, we really wanted to make sure that you perfectly understand the concept of joins since it's so crucial in the daily life of all data workers. This tutorial has 3 parts. In the first part, we'll explore the basic of joins through some small theoretical examples. I'll guide you step by step and you'll have the opportunity to try it out yourself. In the second part, we'll review the join again with a very simple real-life example. This hands-on approach should make the ideas clearer and help you grasp the core concepts. Once we have a good grasp of join, we'll move on the last part of the tutorial. Here, we'll dive deeper and apply our knowledge to answer some real practical use case questions using the TMDB movie database. By the end of this tutorial, you should have a solid understanding of the concept of joins. Let's start the first part of these lessons. Here, we'll review how different types of joins are working. First, the left join. Second, the inner join. Third, the full outer join. Fourth, the different join, A minus B. Fifth, the exclusive OR join, A XOR B. And the last one, the sixth, the cross join or cross product. These are the 6 most common types of joins that you'll find inside almost any data science or analytic project. There also exist some more exotic joins that we will review in another more specialized video. To start, you should actually already have an idea on how these joins are working since we already briefly talked about them inside the part 8 of the Anatella basic tutorial. If you're already familiar with joins, please feel free to skip directly to the last part of the tutorial by clicking the chapter name TMDB use case inside the comments here below. This is where we'll dive into answering specific interesting business questions using join operations. So let's begin. Let's right-click on the simple join box and select the first option named Real Life Examples. For our first example, here we'll be using 2 tables, the product table here and the franchise table here. This table have many columns, but there is one column that is a little bit special. It's the primary key column. The primary key column is a column that uniquely defines a specific row inside the table. Here, our primary key columns are IDP for the product table and IDF for the franchise table. IDF stands for ID for franchise table. So, when I am talking about this very specific row with the X-Wing model inside the product table, I will simply say, look at the row number 2 in the product table. That is because the primary key is 2 inside this very specific row. And when I talk about the row number 2, there is no ambiguity. It is 100% sure that I am actually talking about this very specific row and no other one. The primary key is also a very important notion when talking about join. So let's focus on join again. More precisely, let's explore the left join, also known as the left outer join. In a left join, we combine all the rows from the left table or master table with the matching row from the right table or slave table. Here, our master table is the product table and our slave table is the franchise table. We combine these two tables using two common columns. In technical terms, these two common columns are named keys. One of these two columns is named the primary key and the other one is named the foreign key. More precisely, the two key columns that we'll use for this join are the column franchise ID inside the master table and the column IDF inside the slave table. We already talked about the column IDF a little bit earlier. We explained that the column IDF is the primary key of the franchise table and it's also the primary key of our join here. We didn't talk yet about the franchise ID column. We just said that this column is one of the two key columns used inside our join. More precisely, in the context of our join, the franchise ID column is our foreign key. Inside the join, the primary key is always inside the slave table and the foreign key is always inside the master table. You can see here the table that is the result of the left join operation between the product table and the franchise table. Now, you might be wondering, how is this result table is actually computed? The output table of a left join is a table that is almost an exact copy of the master table A. Inside our little example, the master table A is the table with all the products. The small difference is that this output table contains a few more extra columns compared to the master table A. These additional columns are coming from the slave table B. How do we compute the content of these extra columns? Let's take an example. Let's look at the row with the Iron Man toy. The same row appears inside the output table of the join. On this row, the foreign key is 2. This means that inside the slave table, we must also look for the row with the same value 2 inside the primary key column. This is the row about the Marvel franchise. So, this means that inside the output table from the join, we will get the value Marvel inside the franchise column. The principle is simple. We search inside the slave table for the row where the two keys, the foreign key and the primary key, are matching. And this gives us the content of all the extra columns inside the result table from the join. In our example, our primary key and the foreign keys are matching each other on the first 5 rows inside the product table. But when there is no match between the foreign key inside our master table and any primary key inside our slave table, then we find some null value as output. Did you notice that for the last row of the product table, we get some null values as output? That is because our foreign key value number 4 does not match any primary key from the slave table. The null value is a very important notion inside any data management tool. It represents the total absence of information. Here, it means that we basically know nothing about the franchise from the teddy bear product. Inside Anatella, the null value is represented by a cell with a pink background. The left join always makes sure that we get as output all the records from the master table, even if there are no matches in the slave table. Feel free to explore and experiment with joins using the example graph. In the properties of the simple join box, you'll find the type of join option. This allows you to select the specific type of join that you wish to perform. You can also indicate whether the primary key of the join is unique or not. Most of the time, the primary key column of the join is unique, meaning that each row of the primary key contains a different value. But there exists some uncommon situation while the primary key of the join does not have this unique property and contains the same duplicated value on several different rows. You can select here a type of join that supports this uncommon situation. We very often encounter join operation when manipulating tables coming from relational databases, such as MS SQL Server, Oracle, Postgres, and etc. Inside the database world, the best practice is to split data into multiple different tables. This practice is known as data normalization. It helps eliminate redundancy in storing data. But the real main advantage of data normalization is that it guarantees data consistency for all the data stored inside the database. For example, let's go back to our product and franchise example. We could create a database with a single table instead of our two tables. But then we could easily introduce inside our database some errors, like on this row. Here, we didn't write Star Wars properly. Now let's move on to the inner join. The inner join is actually doing two operations at the same time. It's simultaneously doing a join operation and a filter operation. The filter operation just excludes all the rows that don't have a match in the sleeve table. We use an inner join when we want to retrieve only the records that have matching key values in both tables. This helps us to focus on the shared data between the tables and exclude any non-matching rows. In our example, the inner join gives as output a table that only contains 3 rows. These are the 3 rows related to the lightsaber, Grogu, and StarCraft products, as these are the ones that have a matching price. The product bike is excluded from the output since it doesn't have a matching price in the price table. The different joins, also known as A minus B join, retrieves the row that exists in the master table A but not in the sleeve table B. It finds the unique rows in the table A that are not present in the table B. In our example, the result of the A minus B join is a table with the bike product, as it doesn't have any corresponding price in table B. The XOR join, or exclusive OR join, returns the row that exists in either table A or table B but not in both. It helps us identify the unique row that belong exclusively to either table A or table B. In our example, the XOR join returns the product bike as it doesn't have any corresponding price in table B. And from the sleeve table B, we get the row with ID number 5 as there are no product associated with it in our master table A. The full outer join combines all the rows from both the master and the sleeve table, including both matching and non-matching rows. If there is no match, null values are filled in for the columns of the non-matching table. It gives us a full and a complete picture of the data from both tables. You can think of it as the full universe of join operations, as all the other type of join can all be obtained by applying a filter on the result of the full outer join. For example, if we remove from the output all the rows that have a null value, it becomes an inner join. A cross join, also known as a cross product, combines its row from the first table with every row from the second table. It generates a Cartesian product, resulting in a very large result set with all the possible combination of rows. It is important to use cross-join with caution, as they can quickly create a vast amount of data. In this example, the table A has 4 rows and table B has 3 rows. So the resulting table has 12 rows, 4 multiplied by 3. Cross-joins are useful when you need to generate all possible combination of rows between two tables. So here is a slide that summarizes everything that we have seen so far. We have seen 6 different types of joins. The 3 most common joins are the left join, the inner join, and the full outer join. The less common type of join are the cross product join, the I minus B join, and the XOR join. All these joins require 2 columns to operate, a foreign key column and a primary key column. The foreign key is inside the master table. The primary key is inside the slave table. Most of the time, the primary key of a join is unique, meaning that there is no duplicate value inside the columns. When the 2 keys, the primary key and the foreign key, do not match, we'll get as output some null value that represent the total absence of information. Inside Anatella, the null value is represented by a cell with a pink background. Now that we have seen how each join works in a purely abstract setting, let's come back to each join and explain how it can be used in practice using a concrete small example. Let's start with the most common join, the left join. Inside this example, let's assume that we are working for a web shop and we have 3 tables inside our database. These 3 tables are describing all the purchases inside the web shop. The question that we ask ourselves is, which customer buy which product? To answer this question, we need to link the customer table with the product table. But there is no direct pair of keys that link this table together. To link the customer table with the product table, we need to use the order table. More precisely, one order is composed of several products purchased by a customer. You can clearly see that here. The order number 1 is about the customer 101 that purchased the product P1 and P2. So using the order table, we can link the customer table with the product table. More precisely, we link the order table with the customer table using the customer ID, and at the same time, we can link the same order table with the product table using the product ID key. Once all tables are linked together, we can see, for example, that Bob bought a camera. In technical terms, what we just did is to denormalize the data to get one big flat table instead of dozens of small tables. This big denormalized table is typically very useful to do analytical tasks such as machine learning and business reporting. You might have noticed that we use 2 different types of boxes to compute our left join, here and here. Most of the time, you will be using this box, the multi-join box, because it is faster and easier to use. But there exists some special situation where you'll be forced to use the other box, this one. For example, when the primary key inside the slave table is not unique, or when the slave table is very big, like several gigabytes, then you are forced to use the simple join box instead of the multi-join box. Let's investigate another join, the inner join. Here, we ask ourselves, who are the customer with a known address? To answer this question, we join together the customer table with a second table that contains the addresses of our customer. Please note that inside the output table, we don't have the customer 102 because his address is unknown. Indeed, the foreign key P2 is visible nowhere inside the address table. Let's investigate another join, the A minus B join. Inside this example, let's assume that we are working for large retailer. Here we ask ourselves, which products are not purchased very often and can be removed from the shelf to make some space for more profitable products. To answer this question, we have two tables. The first table is a table that lists all the products inside the shop. The second table lists all the products that were purchased recently. Basically, the second table contains the list of products that we want to keep. So when we remove from the first table the product from the second table, we find all the bad products that can be removed from the shelf. For example, the product 3 has not been sold recently and should be dropped. Let's investigate another join, the XOR join. Inside this example, let's assume that we are working for a human resource department inside a big company. Here we ask ourselves, I'd like to find the inconsistency inside my HR database. More precisely, I'd like to find all the projects without any assigned employee to work on them and all the employees that were not assigned to any project. So, we have two tables, the employee table and the product table. These two tables are linked together thanks to the key named employee ID. Let's do an XOR join between these two tables. We can see that the employee number 5 does not exist, but he was still assigned to the project E. That's odd, isn't it? Similarly, we can see that the employee 7, Alex, has no assigned project. What is he doing? Nothing? Strange. Let's investigate another join, the full author join. Inside this example, let's assume that we are working for a company selling subscriptions. Here, we ask ourselves, what is the net revenue per customer? All the customers can subscribe to two different services. The subscription for the first service are given inside this first table, and the subscriptions for the second service are given inside this second table. Both of these tables have the same structure. The first column is the primary key of the customer, and the second column is the revenue generated by the subscription for a particular customer. Instead of two separate tables, we start by creating one single big summary table that contains the revenue for both subscription for each subscriber. In this case, we must join the two tables using a full author join, just to be sure to never lose any revenue for any customer. Once we have our single table, we can compute the net revenue for each customer. The net revenue depends on the margin that we make on each subscription. For the first subscription, the margin is 50%. So we multiply the sales value by 50% to get the net revenue generated from the first subscription. And we do the same for the second subscription, except that this time the margin is only 25%. Then we sum both net revenue for the two subscriptions to get the final total net revenue for each customer. Please note the NVL function here. It just replaces the null value with a 0. If we don't use the NVL function, most of the computation will result in a null value. Let's investigate another join, the cross-product join. Inside this example, let's assume that we are working for a big web retailer with several warehouses. Here we ask ourselves, what's the distance between each of my customer and the closest warehouse? First, let's compute all the different pairs of warehouse and customer address. To compute all these pairs, we just join the customer table and the warehouse table together using the cross-product join. Then we use the calculator box to actually compute the distance in kilometers between the customers and the warehouses for each pair. Then we use the aggregation box to compute the smallest distance for each customer and we get our answer. The problem with this approach is the gigantic size of the table that goes outside the cross-product join. It's huge. This means that this process will be extremely slow because it typically has to compute millions of distances. I would advise you to rather use the KNN box to solve this question, because this box use clever mathematical properties of distances to avoid computing 99% of the distances, thus providing a response much more quickly. So, we just finished now the first part of this lesson about join. You should now have a clear understanding on how the different join operations are working. In the second part of this lesson about join, we'll use our newly acquired knowledge about joins to solve some real-world complex business question on the TMDB database. I hope that you enjoyed this video. Give it a thumbs up by hitting that like button. Your support means a lot to us. If you want to see more amazing content like this from us, make sure to subscribe to our channel. Don't hesitate to tell us inside the comment below how we can improve these training sessions around data preparation. In the second part of this lesson, we'll use the TMDB database to answer some really cool questions about the movie industry. We'll find the answer to 8 different questions such as which movie genre generates the highest profit, which actor frequently collaborate and appear together in movies. This will be really fun. To access the second part of this lesson about join, I invite you to click here. Talk to you soon. Bye.